Speaker of the afternoon is Davide Cassani, who will tell us about gravitational saddles.
Thank you, Finn. Good afternoon. Let me start by thanking the organizers, in particular Vineet and Leo, for the invitation and for setting up this nice workshop. So the topic of the talk will be the five-dimensional gravitational index and its saddles with different topologies. And this is based on work done in collaboration with two great collaborators, Alejandro Ruiz Perez and Enrico Turretta. Alejandro will soon be back to Padova as a postdoc, and Enrico was my graduate student and has now moved to Seoul in Korea. So I apologize to those who already attended a version of this talk, but I'll try to make some comments on possible developments and work in progress while we go. So in the spirit of the workshop, maybe this will trigger some discussions. So please don't hesitate to interrupt me at any time. So let me start by reminding you of a very robust partition function that is refined with an index. This is a trace over in the Hilbert space of the theory of -1 to the f, where f is the fermion number. And then we have a supersymmetric Hamiltonian defined by the anticommutator of two supercharges. And then we may refine this basic index by adding chemical potentials for some charges that commute with the supercharge. So only supersymmetric states contribute to this partition function. That's why it is so robust. And in particular, it is invariant under different any continuous deformation. In particular, it is an RG flow invariant. And it is independent of the inverse temperature beta appearing there, precisely because only supersymmetric states contribute. So this can be used to explore quantum gravity. Indeed, any successful black hole microstate counting eventually is based on a version of these indexes, so it's based on an index computation, and in one way or another uses a version of holography where the quantum gravity partition function is mapped into a conformal field theory partition function where we know, at least in principle, what is the Hilbert space and what is this trace that in principle is not so well defined in gravity. So our aim today will be to define and study this gravitational index directly in supergravity, not by using the Hamiltonian trace, because we don't know what's the Hilbert space of the theory, but using the gravitational path integral. So the gravitational path integral is just, as everybody knows, it was introduced by Gibbons and Hawking, and at least formally, it is a sum over all possible matrix plus other fields satisfying some given boundary conditions. Of course, boundary conditions are very important. Here we are dealing with non-compact spaces, so it is important to fix boundary conditions. Of course, defining and computing this object is very hard, but we will be happy with working with a semi-classical approximation. So for the purposes of the talk, we will just be concerned with defining and finding and classifying possibly the possible saddles of this object, and perhaps trying to compute their action, so the saddle point action, so that we know what's the contribution to the partition function, and perhaps compare the different saddles once they are classified. So saddles are, of course, classical solutions with a given finite and Euclidean action. They should, of course, satisfy the boundary conditions that we are going to impose. So what's the theory we are going to consider? We will focus on five-dimensional supergravity. I will restrict to the minimal theory, that is just the supergravity multiplet. This is a theory of Einstein-Maxwell theory with a Chern-Simons term that is crucial for supersymmetry. Of course, there is also a fermionic part that we will not consider. And for the purposes of today's talk, there will be no cosmological constant here. Dario, in the next talk, will discuss a similar topic, but we will see there will be a cosmological constant, so there will be some differences. So one good thing of working with ungauged supergravity, that is the theory with no cosmological constant, is that a lot of things are known about solutions, the supersymmetric solutions. They are being classified, and they allow for many different possible topologies, which will be the main focus of today's talk. So again, the context of the talk is five-dimensional supergravity with no cosmological constant, And the main motivation is that many topologies are allowed. For instance, if we consider BPS horizons, these have been classified and realized in explicit solutions. So we can have an S3 topology. This is the horizon topology of the BMPV black hole, as well as of its non-rotating version, that is the Strominger and Waffa black hole. Then we may have an S2 times S1 topology. This is the topology of a black ring. This is also explicitly known. And okay, here it's not really visible. We can also have a more exotic lens-space topology that is an orbifold of S3 that is classified by the rank of the orbifold, that is by this integer p. There are also horizonless solutions that have been constructed, and they also play a very important role, in particular in the fuzzball proposal. So there are solutions that have a non-trivial topology. So there are two cycles appearing in the domain without any horizon, but still there is this topology, and there are fluxes through the cycles that support the non-trivial topology. So they are sometimes called topological solitons or bubbling solutions, precisely because one can have an arbitrary number of these bubbles. One can also have combinations of these two types of solutions. That is, one can take a black hole and put it in the background of a topological soliton. And these solutions, as we are going to see, can be constructed systematically. So these solutions can also be compared. So if we are in the microcanonical ensemble, we fix the charges and then compare the entropies to see which one dominates. So in 5 dimensions, as it's well known, fixing the asymptotic charges is not enough for determining the solution uniquely. So given the charges, we can have different solutions that compete. In particular, we can have the BMPV black hole and these topological solitons sharing the same charges. And so this is a main motivation for considering these topological solitons as possible microstates of the black hole. And also there are black objects, so objects with a horizon, that have the same charges as the BMPV black hole, but a larger entropy. This was first emphasized in this paper. These black objects are these black holes in the background of a topological soliton. So there is non-trivial topology in the domain of outer communication. And in some regime of the parameters, these solutions can have a larger entropy than the BMPV black hole. So all these statements are in the microcanonical ensemble. I just gave some examples of possible statements that can be done in this ensemble. However, the partition functions that play a role in the black hole microstate counting, at least originally, are defined not really directly in the microcanonical ensemble, because they typically depend on some chemical potentials or fugacities. Consider, for instance, the elliptic genus, depending on the modular parameter of the torus in 2 dimensions for the two-dimensional conformal field theory playing a role in the Strominger and Waffa story. So we are interested in considering partition functions that are not directly, immediately microcanonical. So some of these have, so there are some fugacities playing a role. And the questions we ask are whether we can study and compare solutions with grand canonical boundary conditions. And then we ask, which solutions dominate? Are there phase transitions between them? Can we learn something new about quantum gravity from this perspective? So in order to define these grand canonical boundary conditions, let me show how we can introduce these chemical potentials. And in order to do so, I'll also fix this slide will also be helpful to fix my notation that I will use for the rest of the talk. So I will consider asymptotically flat space with compactified Euclidean time. And so the asymptotic metric will take this form. This is just the asymptotic metric. And this is helpful just to show some of the isometries that will play a role in the rest of the talk. So here we have the Euclidean time tau, and then there is an S3 parameterized with these 3 Euler angles as in a standard way. And the identifications that are chosen between these angles are such that this describes indeed an S3 topology. So given these isometries, the isometries will be parameterized therefore by tau, phi, and psi. We have 3 isometries. And then since we are in this supergravity theory with a gauge field, we also have the electric charge. So we have these conserved charges, E, J+, J-, and Q. J+ and J- are associated respectively with rotation along phi and psi. And then we can introduce their conjugate potentials, that is the inverse temperature, the angular velocities omega plus, omega minus, and an electrostatic potential phi. The way they are introduced, we can introduce them in different ways, either as background fields or as boundary conditions for the identifications of the fields. Let's do the second approach. Let's take the second approach. So these angular velocities are introduced by claiming that the coordinates are identified in this way. That is why we go around the thermal circle once. The other two angles, phi and psi, are also advanced by these angular velocities, omega plus and omega minus. The electrostatic potential is introduced in a standard way as a gauge holonomy for the gauge field we have. This is the gauge field in the supergravity theory. Here I'm introducing a shift that will be convenient for me. So this is the basic setup for introducing my boundary conditions. And the main point that will be important in the rest of the talk, sorry for the slides. Maybe I'll move to the PDF version. Okay, it is better. Okay. So a main point of the talk will be to use these three isometries. So having claimed that the coordinates are identified in this way here and there, an equivalent claim is to just declare that the isometries that have closed orbits, in particular closed 2-pi periodic orbits, are these three Killing vectors here. So these three Killing vectors may collapse in the bulk. Some of them actually also collapse, given the boundary conditions that I took, they actually collapse also at the boundary. So there are these two isometries. This is a U1, this is another U1, that collapse in the asymptotic tree-sphere. They are the two U1s that collapse at the two extrema of the interval by which I can define this tree-sphere. The remaining circle, the thermal circle, does not collapse at the boundary, but it may collapse in the bulk. In this case, we would have a Euclidean horizon. However, in our case, we will have combinations of these isometries, and each of these combinations may collapse or not somewhere in the bulk, and this will play a role because it will define some fixed points, some fixed locus that may contribute to the action eventually. So if we fix the Dirichlet boundary conditions, we have this grand canonical partition function. Here I'm using the superalgebra to define this supersymmetric Hamiltonian. And we want a partition function that only receives contributions from supersymmetric states in order to do so. So this is not the case in the original partition function here. Even if I'm using this anticommutator of the supercharges, this receives contribution from all possible states. However, if we fix one of the angular velocities so that we can trade one of the angular momenta for -1 to the f, where again f is the fermion number, then formally this trace becomes a Witten index precisely of the form that I introduced at the beginning. So this condition here can be seen as a supersymmetric boundary condition that should be satisfied by any saddle that contributes to this partition function. And this will be the way we construct our gravitational index from the Lagrangian point of view. So we don't really know how to define this trace in the quantum gravity theory. However, at least semi-classically, we can impose this boundary condition in our path integral and therefore in any of the classical solutions that we will consider. And this will be interpreted, if it has a finite action, as a saddle of our partition function. So this is my definition of the gravitational index, and we expect it has all the nice properties of the Witten index. So the Laplace transform if we pass from the formulation with chemical potentials to the one with fixed charges, gives the degeneracy. The degeneracy is at fixed charges, that is the entropy. And in this way, we can provide a microstate counting for different black holes, and which can be compared with microscopic approaches. So this story has been successful both in asymptotically flat and asymptotically ADS case, in particular for the asymptotically ADS case, with the comparison with the dual superconformal field theory defined asymptotically has been the object of a large activity in the last decade or so. And it has given a microscopic derivation of the ADS black hole entropy in a number of examples. So here we will focus just on the asymptotically flat case. So there will be no holography, at least to start with. However, we still want to explore this gravitational path integral and see what are the possible saddles. So the question we want to answer is, what are the saddles of this gravitational index? Well, there should be supersymmetric solutions, because as we said, any solution that contributes to this partition function should respect supersymmetry. They should be Euclidean, or at least have this compactified Euclidean time. And they should have a finite beta, because in order to contribute to this partition function, well, at least this is at least originally defined with a finite beta, although eventually the result does not depend on beta. So we are also free to tune beta in different ways. Sorry. So it should have these requirements. However, a solution with supersymmetry and finite beta in Lorentzian signature would not be well defined. It would have all sort of pathologies because it is so having finite beta, it's non-extremal. So as a Lorentzian solution, these saddles are not well defined. However, if we allow for a complexification, we can accept them as saddles of this Euclidean partition function and see if they lead, if this picture is consistent and they lead to sensible answers for at least for the entropy and for the contribution they may give to the partition function. Eventually, we are free to send beta to infinity and therefore recover solutions that also make sense in Lorentzian signature because they become extremal, so they would be supersymmetric and extremal. And therefore, by this approach, we can interpret Lorentzian solutions as saddles of the gravitational path integral in this limit where beta goes to infinity. So before going to this Euclidean complexified regime, I should remind you some well-known things from more than 20 years ago. That is, how are these supersymmetric solutions constructed in Lorentzian signature from scratch. So supersymmetric solutions always have an isometry. In this theory, five-dimensional supergravity, always have an isometry. So they, in particular, I'm focusing on a time-like class where this killing vector is time-like. Here I'm considering its Euclidean version. And we will require, there is at least another isometry. Eventually, we want to have 3 U1 isometry. So if we require just one more isometry, that I denote by del psi, then all these solutions are determined by harmonic functions in R3. So there is a nice construction that is systematic and it allows superpositions of different solutions. This is the local form of the matrix. This is the local form of the gauge field. The details are not very important. Just you see there, this is a time-like vibration over for the space of the Gibbons-Hawking form, which also is a vibration over R3. So the important thing is all this, the whole solution is determined by harmonic functions. Here the functions are h and k. There are also 2 other functions, but they are fixed in terms of these ones in the present context. So these functions are harmonic in R3, so they have this form. R is the distance from some special points that are called centers. And here we have some parameters that in our case will be complex in general, but in the original Lorentzian solution they are real, and they should satisfy some constraints. So all the rest in the context I'm going to discuss will be fixed by regularity. So all we need to know is that there are these harmonic functions. So we will also impose an additional requirement. This is really some simplification that we want to have, but it's not really needed. We impose a third U1 symmetry, because these are the symmetries we have asymptotically, so we would like to have them in the bulk as well, at least for simplicity. So we impose that in R3 there is also another U1 symmetry, so we have U1 cube in total. And this means that in R3 everything will be, we have this cylindrical symmetry because we introduce this additional U1. So all the centers will be aligned along an axis. So in this, there are a number of parameters, as you have seen. We have 2n minus 2 harmonic functions coefficients. There are these 2 n minus 2, these coefficients here, h and k, with the constraint. And then there are also the distances between the different centers that are n minus 1. So in principle, we have 3 n minus 3 parameters, but then some of the solutions, some of the parameters will be fixed by either regularity or by some equations that are called bubble equations. So what are the properties encoded by all these parameters in general? Well, of course, this will encode the conserved charges. So we have Q, J plus, and J minus. There are 3 conserved charges. But of course, as we said, fixing these charges is not enough for fixing the solution. There is something more. And this something more is called a rod structure. So a rod structure is this structure based on intervals between the centers of a supersymmetric solution. And these intervals will be denoted by this capital I. And so these are the rods. And the rods correspond to, they are characterized by which isometry degenerates at these points, over this interval. So these rods are associated with rod vectors, or vice versa. To each of these rods, we can associate a rod vector. So there is a combination of the 3 U1s that we have in the game that degenerates on each of these rods. And on each of these rods, we can have a different combination that degenerates. And this gives rise to the different non-trivial cycles that we can have in the solution. So let's consider one of the most basic examples. That is a solution that has just 2 compact rods. That is, it has 3 centers, 2 compact rods, I1 and I2. This can be generalized in a much more complicated way, as shown, for instance, by Ben and Warner. So we can have a look at, on each of these rods, so these are considered at a fixed time. So we have a 4-dimensional space. There is a U1 that collapses. So the fixed locus is a 2-dimensional surface. And so this is, in general, it is not smooth. But if we fix these parameters in this way, so these h's are either +1 or -1, then we have smooth S2. So the fixed loci for each of the isometries is just an S2. It is given by the coordinate along the rod times the remaining U1 that is not collapsing. There is a question?
Can I compare this with like the, just at a fixed time slice? Is this kind of like the multi-center Uguchi-Hansen construction, or is this, written in Gibbons-Hawking form? Is this the same?
Yeah, it's similar. Here, it's a fixed time, so we forget about the time coordinate. We are left with the 4D space. It's the 4D Gibbons-Hawking base, and yeah. Okay, this can be generalized in much more complicated way. So you can add an arbitrary number of rods, and you create these topological solitons I was talking about before. It's also interesting to consider the case where these coefficients are not 1. So they must be integer in order to avoid Misner-Dirac strings, but they may not be 1. In this case, we create conical singularities. So the fixed surfaces have conical singularities at one or at both poles. And in this way, we introduce into these bubbling solutions these surfaces that are known as teardrop or spindle that also play the role in holography, as Dario and collaborators have shown recently. So this Benau.
Is the full space-time there like an AN singularity, or? Is the full space-time there at these singularities C2 mod CH, or is just one copy of C? 2 copies of C or 1 copy of C? It's just the full 10-dimensional space-time.
Yeah, you may also have singularities. So you have the collapsing U1. This may also have orbifold singularities in general. So this is the singularity that is describing how, so this surface has this singularity, but then on top of it you have the collapsing U1, and that collapsing isometry may also have conical singularity.
Has to have another singularity so that the whole thing is just
it's R4 mod Z.
Okay, yeah, that's what I was asking.
Yeah. Okay, but we are mostly interested in cases where there is a horizon. So in these Lorentzian signature horizons are also part of this construction, but they are isolated points. So they do not correspond to a rod, but they correspond to an isolated point. the vector that degenerates at the horizon in a supersymmetric solution is this del tau that is the supersymmetric Killing vector, that one that follows from the fact that there is supersymmetry. So this diagram here is the representation of the BMPV black hole. There is an horizon, this vector collapses, and here and there, over these two intervals, semi-infinite interval, the vector that collapse are those that also collapse at infinity, so they are the U1s that are in the S3 that also collapse at the horizon. So this horizon, this diagram also represents an S3 topology, so it corresponds to the BMPV black hole. We may be interested in more complicated topologies, so we should consider horizons with a non-trivial rod. So if we consider this other diagram, so we have an horizon here, that is the vector that collapses here is again the time-like Killing vector. But we declare that along this red rod here, the vector that collapses is not the same one that collapses at infinity, it is del phi plus del psi, but is again the same vector that collapses on the other side, at the other pole of the horizon. So this represents a black ring. Why is that? Because we see that at the horizon, the vector that collapses at the two poles is the same. So we are describing an S2, where the vector that collapses at the two poles is the same phi isometry. While the other one is not playing a role. So we may ask, what is the topology of this fixed locus corresponding to this vector that collapses? In this case, sorry, I skipped this. So, and this is a disk topology. So we can also introduce non-closed topologies by this construction. So this is what a black ring would be from this point of view. We can also have the black lens, as I anticipated before. So simply we must consider a different vector that collapses here. This is an example. So this is the black lens with the L21 topology that was first constructed by Kundura and Lucetti. The full solution is explicitly known. Here I'm representing it through this diagram, this simple scheme, but the full solution is known, the action, the metric is known, the gauge field is explicitly known, and it's based on this construction that I just presented. So we can go on and combine rods with non-trivial topology, with horizons, and in principle construct more and more complicated solutions. These have been classified in Lorentzian signature. Also, it is important to remind that we also need to specify the gauge flux through these two cycles. And this gives some additional data that should be specified in order to fix the solution. As I mentioned, we can also have combinations of these rods that may be horizon or bubbling rods. Again, let me emphasize again that these solutions may play a role in the microstate counting because some of them can have the same charges as the BMPV black hole and the larger entropy, so they may dominate the microcanonical ensemble if they contribute at all. And so this may be a puzzle for some microscopic match, as it was emphasized in these papers. However, the scope of this talk is to consider saddles of this grand canonical supersymmetric index. So we should consider versions of these solutions. First, we should assign chemical potentials and non-trivial action to these solutions. And we cannot do this on the nose because the solutions are so far defined in Lorentzian signature. They are extremal. They have an infinite throat, so defining what is the action is not a priori well defined. So we will deform them into supersymmetric non-extremal solutions in the sense that I presented before. So the way to do this, again, coming back to this simple diagram, is to make these horizons that are supersymmetric and extremal just non-extremal by maintaining supersymmetry. This has been done in a bunch of papers, including people in the audience have contributed to this. Here I'm sticking to this 5-dimensional perspective. So let's start again from the BMPV black hole. If we want to have a non-extremal version of that, we should make the rod that corresponds to the horizon finite. So this delta is related to beta. If delta goes to 0, the distance between the two extrema of the rod, of the horizon rod, if the distance goes to 0, that is delta goes to 0, then beta would go to infinity. There is an explicit relation that we can recover by studying the solution. So we should have finite horizon rods. And then the vector that collapses here is the thermal Killing vector that I introduced before. I declare this is a U1, this has closed orbits, and I declare that this vector collapses along the horizon rod. You see that if beta is going to infinity while the other two remain finite, this would dominate, so this also matches the fact that if I can take an extremal limit of this deformation and come back to the Lorentzian solution. But here I want to deform the solution in this Euclidean non-extremal regime in order to be able to assign chemical potentials. As you see, I introduced them here, and compute the Onshel action. So the parameters in this case, where I have just a finite rod with two parameters h's, I have a k because so these h's were constrained by the fact that the sum should be 1. So I have a bunch of parameters. It's not the details are not important at all, but I just want to say that they can be traded explicitly for the chemical potentials that play a role for us. So this beta, omega plus, omega minus, and phi. And in particular, you see again that if delta vanishes, beta will go to infinity. So in this way, we close this horizon rod and recover the extremal Lorentzian solution. So this is the deformation we want to consider. And we can play the same game for the other solutions, and I'm going to do that in a moment. But having done this, we can now compute the Onshel action of the solution. The solution is nicely capped. There is no infinite throat anymore. So this can be computed. And the result we obtain is this one. It's not so surprising because it's the same expression that is also obtained when you compute the action of the ADS5 black hole that also gives the correct entropy after Legendre transform. However, here we are in the asymptotically flat context, but the form of the action is exactly the same. What is different is just the constraint satisfied by these chemical potentials. In this case, recall the constraint that I imposed is this omega plus, that is the sum of these two omega 1 and omega 2, is 2 pi I. So that's the constraint I impose. In asymptotically ADS, it would be slightly different, but the rest is the same. So the form of the action is the same in the two cases. Can be computed in a number of ways, also via equivariant localization, but this will be the subject of Dario's talk. One way to compute it, in this case, we have the explicit solution, so we can just compute it by an explicit computation. In the asymptotic ADS case, things may become more involved, especially if you consider more complicated topologies where the solution is not explicitly known. So we can compute the Legendre transform of the solution. This is a well-known story. So we compute the Legendre transform of this Onshel action. You recover the correct entropy of the BMPV black hole after imposing that this entropy is real. And the reality condition corresponds to fixing one of the angular velocities to 0, as it is in the BMPV black hole. Just an aside comment here, if the parameters of the solution, if I insist with the metric being real, I'm forced to consider chemical potential and charges that are purely imaginary, so they would not correspond to the charges of the BMPV solution when I take the extremal limit. And so this is too restrictive for us. So we consider different reality conditions on the parameters that imply that the metric must be complex. However, this allows us to fix real charges. In this case, the entropy, the action is also real, but that's an accident of the solution. In this way, by taking the beta to infinity limit, we can directly match the Lorentzian solution with real metric and charges. But the scope of the talk is actually to go beyond this black hole case and explore more topologies, more different saddles that only exist in this 5D scenario. So let's come back to the rod diagram that represents the black ring or the black lens as well. Remember, there was an extremal horizon here where the collapsing Killing vector is this one, and then there was a rod where the collapsing Killing vector is space-like. Again, the game we should play is to go to deform the solution to finite beta. So we create a rod of finite size, where the collapsing Killing vector is again this thermal Killing vector. And then, depending on what other Killing vector collapses here, we can have different topologies, different horizon topologies and different bubble topology. By bubble topology, I mean the topology of the fixed locus in this rod outside the horizon. So I'm not going to present the full solution, but again, it can be constructed based on the systematical construction that I just presented. Again, we have a bunch of parameters that we can trade for some physical data, that is the chemical potentials. And in this case, we have an additional datum, because you see, we have, in this case, we have more parameters because we have 3 centers. It's a solution with 1 extra center, so there are more parameters associated with this center that I'm calling the parameter H1. So we have the chemical potentials. Again, you can check directly in the solution that one of them is fixed in order to satisfy this constraint that for us is the boundary condition for the solution to contribute to some index to be defined more properly. Then some of the other parameters can be traded for these chemical potentials that are non-trivial and in principle complex. And finally, we have to provide an additional datum that is this capital phi that also appears in this expression for the action. And we define it in this way. So for each of these rods, we have a collapsing Killing vector. The Killing vector that collapses forms a cigar. So there is a radial direction and the U1 that collapses. This is this Ni. This represents this normal bundle to the fixed locus. And we integrate the gauge field F over this, and this gives for us this capital phi. We call it bubble potential. In the case of the black ring, this corresponds to the dipole charge, but more generally, this is not exactly the same. So this is an information that appears in the on-shell action. Again, this can be computed explicitly, knowing the solution. We must be careful because the gauge field is not globally defined here, so we have to compute the action. Since the action contains a Chern-Simons term, it is dependent on the gauge, so we must be careful with defining the whole integral patchwise. But after doing all this, you reach a result for the on-shell action that depends on the chemical potentials. These are fixed at infinity. On this additional information, the phi that I define here. And then there is this parameter H1 that is must be an integer, as I said before. For the black ring and black lens, it should be either +1 or -1. But more generally, if we allow for conical singularities, it should just be an integer. For each of these saddles that we have constructed, we have the on-shell action. So in principle, we have the contribution that the saddle will provide to our partition function. So let's say in particular the form of the expression for the black ring and black lens. So these are those that once we take the limit to the extremal solution, they would give on the nose the black ring and black lens solutions with a smooth horizon. So the form of the action for the black ring is this one, the form of the action for the black lens is this one. And again, we can play the game of performing the Legendre transform in order to obtain the entropy as a function of the charges. And again, we find that on the nose, this matches the known expressions for the entropy of the black ring and black lenses that have been constructed explicitly in Lorentzian signature. So in this way, what we have done is by this deformation, we have been able to provide chemical potentials and actions for these solutions. So we are able to interpret them as contributing to a grand canonical partition function that is this gravitational index. And we have checked that they satisfy the boundary conditions that should be satisfied for contributing to the index, to the gravitational index. If we want, we can take the extremal limit of these solutions and recover, after Wick rotation, the Lorentzian solutions. So we can continue this game in principle and take, yeah.
Great question. So do you get an analog of this nonlinear charge constraint when you do the Legendre transform?
Yeah.
Do you write it, or
Oh, I didn't write it explicitly because so for the BMPV black hole it's just J plus equals 0, so it's very simple. So it's not nonlinear, it's linear in this case. But in the black ring and black lens cases, you can check that in the Lorentzian solution a more complicated relation between J plus and the other charges is satisfied, and you get it in the same way. That is, you take this action, you Legendre transform it, you impose reality of the entropy, and the reality condition corresponds to precisely to the relation between the charges that is satisfied in the Lorentzian solution. So you also recover that in this way.
Maybe you already said this, but these other solutions, do they contribute to the same index, or do they have different boundary conditions?
It's a good question. In principle, so here I'm defining my index asymptotically in the asymptotically flat regime. So they satisfy the same boundary conditions in the sense that all of these have omega plus equal to pi I, so they in principle contribute to an index. And they also carry the same type of chemical potentials that are these ones. Now, if the value of the chemical potentials can be the same so that they compete for these fixed chemical potentials is to be seen. Because, for instance, for the black hole, these chemical potentials must be real if you want to have real charges, while for these black rings, they exist in different regimes of the chemical potentials in principle. But there may be overlapping regimes. This is something we have not really studied in detail, but in principle, they may compete in this grand canonical ensemble. And I'll maybe make some more comments at the end. So one could add more and more horizons. This is something that can be done. Or we can also do something else, that is take a limit of this solution that has a non-extremal horizon, this blue rod, plus a bubble outside of it, this red interval, so that the solution becomes horizonless. So we take a limit of this complexified solution with the horizon that connects to the horizonless solutions. How can we do this? Well, you see, this Killing vector that collapses here can become space-like if beta goes to infinity to 0. If we just remove this term by taking a limit where beta goes to 0 instead of infinity, this does not contribute anymore. Then we have to satisfy some consistency conditions for avoiding Dirac-Misner singularities. This means that this chemical potential must become chemical potentials divided by 2 pi I must become an odd integer. So if we do that, the solution becomes a solution with no horizon that corresponds to these bubbling solutions that I presented at the beginning. So there is also a limit of these saddles that carry an entropy where the entropy goes to 0, and we can connect to these bubbling solutions that play a role in the fuzzball proposal. But these only appear for these specific imaginary values of the chemical potentials. So it's a question whether this should contribute to the index or not, because they are, in a sense, at the boundary of the domain of definition where these chemical potentials are well defined. There are two questions. Either one.
Just a quick question. So I thought, at least in some cases that I have in mind, whenever the omega can be an odd multiple of 2 pi I, usually it's only one value that is supersymmetric. Here they're all supersymmetric.
No, because you have in mind the case where there is just one omega, the one that I fixed to 2 pi I.
Okay.
In 4D, there is one omega, the one that you fix to 2 pi I. So the other cases would be not supersymmetric. In this case, any value of this omega is supersymmetric because the angular momentum that is conjugate to omega commutes with supercharge. So they're all supersymmetric.
Okay, but sometimes, what I have in mind, maybe you already answered, but like in Reiser-Nordstrom, if you fix beta omega to be...
That's omega plus. The other one that I fixed to 2 pi I, and that's fixed. Yeah. The one that is not fixed is the one, in 5D I have one more rotation, and this commutes with the supercharge.
Okay. Thank you.
Can you also go in the opposite direction and send beta to infinity? What I have in mind is to solve these entropy enigma sort of issues, right? You can offload the angular momentum onto a supertube that lives outside, and then the remaining black hole, since it's lost the angular momentum, has much more entropy. So multi-center things where some of them are black holes, some of them are supertubes, things like that. It seems like in the class of things that you can...
Yeah, they are in the class of things. Here I'm not solving any of these enigmas. I'm just maybe proposing the fact that this can be studied from a different point of view, that would be the grand canonical point of view. This is the new thing in this talk, let's say. That is that you can assign to each of these solutions, horizonless or with an horizon, chemical potentials and on-shell actions, so that you can compare them and study them from this grand canonical point of view without fixing the charges. But I'm not solving any of these entropy enigmas in the sense that there can be, and there are solutions with this non-trivial topology in the domain of outer communication that have a larger entropy than the black hole, the BMPV black hole. So this, I'm not saying anything new about the fact that this is a fact. I don't know if you had some...
Yeah, I would just had in mind there were studies, years ago about resolving this enigma using multi-center bubbling solutions, but ones that had horizons.
Yeah, maybe we can talk later, but I don't have anything new to say about this. So here again, I wanted to emphasize a different limit that can be taken starting from these complexified solutions. One is the extremal limit. The other one is, in a sense, an opposite limit where these solutions are connected to horizonless solutions. And the question is whether in this regime of the chemical potentials, whether these horizonless solutions, that is, these bubbling solutions, they contribute to the index or not. Why is it a question? Because it is a weird regime for defining the index where the chemical potentials become purely imaginary, and also integer after I divide them by 2 pi I. So essentially these solutions will contribute as 1 to the chemical potential because this to the partition function, because omega minus times j just drops out because omega minus is an odd integer. In general, again, these solutions have orbifold singularities. However, there are also completely smooth examples, as it was emphasized first by Ben and Warner. We just need to fix the parameters in a certain way, as described here. So formally, these solutions have the same action as the black ring and black lens, but they are in this regime of the chemical potentials where, if you take the Legendre transform, the action, the entropy vanishes. Again, here I'm emphasizing this question, whether this regime of the chemical potentials is a good one, if we can push the index somehow to this regime where the chemical potentials become purely imaginary and integer multiples of 2 pi I. So the construction can be generalized. The important thing, as I tried to emphasize, is which vectors collapses along this axis and how many of these vectors can collapse. So a vector that collapses must be a linear combination of the 3 U1s that we have in the game. We have this thermal U1 and then the 2 U1s that are realized in the 3 sphere. So we can take a general linear combination. So this is a vector that winds around these U1s in a number of ways, and A gives the number of times it winds around W, and then I have this other integer P that gives me the other possible winding number. All this is constructed so that the coefficient of del phi, that is the isometry that does not commute with supersymmetry, is 1, so that these vectors are always have the good antiperiodicity condition. Apart from that, we have 2 integers that I can introduce, and they give me the winding numbers with respect to this basis of U1s. So I can declare that this is the vector that collapses at a given rod, and then I can change my integers and construct a more complicated rod structure. So I can take, if this NA is different from 0, the killing vector that collapses involves this thermal isometry, so it will form a horizon. If this is 0, it will form a bubble with no horizon. And I can assemble complicated arrangements of these intervals by respecting some rules. The rules can be found by analyzing the solution and imposing some regularity condition, like absence of Dirac-Misner singularities. So, for instance, each horizon rod, these blue rods, must sit between two bubbling rods. We cannot have two horizon rods that are one next to each other. And then the topology of the 3D bolt, that is, now we consider the topology of the normal space of the fixed locus of the U1 that collapses. This fixed locus is three-dimensional because the time also plays a role. So we can study the topology of these three-dimensional bolts. And this depends just on the adjacent rods to the one that we are considering. If we are considering IA, then we have the one before and the one after that. And there are only these two that fix the topology of this three-dimensional bolt. So we have done this study, at least a priori. Then one should construct explicit examples. But so here I have a horizon rod with two bubbling rods next to each other. So I have these integers here that give me which killing vector is collapsing, which killing vector is collapsing. So then we studied the topology of these bolts. The topology of this horizon bolt is a length space topology. So here it is the definition of this length space. It's quite complicated. There is this integer a that is obtained by solving this equation. The details, again, are not important, but what I want to emphasize is that here we have a length space topology that arises. And this can boil down to just S3 or S2 times S1 in special cases if this becomes 1. If we have a horizon rod and no other compact rod, then the horizon is S3 mod Zn, and we have an orbifold solution. So we are constructed just more complicated Euclidean horizons that should also contribute as saddles to the index. So we are introducing families of saddles that depend on some integers. And hopefully they can be helpful to reconstruct some symmetries that should be there. Then we can have bubble topologies. So if we consider a bubble, then this can exist with either just bubbles next to it or a horizon and a bubble. So here I'm giving an example where we have a horizon, bubble, bubble. So I'm studying what is the topology of this bubble here. The topology of the bolt over this interval is, in this case, a bit more simple, and it's again an orbifold of S3. So it's again a length space topology. This can have or not have conical singularities depending on how we fix these integers. Again, we can have either smooth topologies or branched lenses or spheres. So this is the general classification. And then one should figure out if all of these solutions contribute to the index or just part of those. So here I come to my final two slides. In all the examples that I presented, there was one horizon and possibly many rods. We can also have multi-horizon examples. So I gave the rules for constructing them, but then one should also construct them explicitly and maybe compute the on-shell action of the solution. This is not something we have done, except that the on-shell action can be extracted from the quantum statistical relation. So this we can do, but the explicit computation we have done just in the case with 2 or 3 centers. And also there is a recent paper by Boruk and Paran, Iliesio and Murti, where they also consider these multi-horizon examples by uplifting solutions from 4D. So here I'm coming to the outline and to the outlook and the perspective for future work, possibly. Something I've not discussed is the case with multiple electric charges. So, for instance, if you want to study the D1, D5P system, it would be, what one should do is really to consider the case with 3 independent charges. So consider not just minimal supergravity, but supergravity with 2 vector multiplets. So we can introduce three charges. This can be done. Actually, it has been done. these papers. It's also part of our work in progress. Then it would be nice to compute the on-shell action for an arbitrary rod structure. In principle, the ingredients are all there, but since the gauge field is not globally well defined, one has to be careful with the Chern-Simons term. So technically, it is non-trivial, a non-trivial computation. However, it can be done. The technology is also there, because the technology of equivariant localization, that will be a main topic of Dario's talk, will be helpful here, because we just need to understand what are the contributions of these fixed loci where the different Johann-Killing vectors can collapse. And once we have them, we can probably just add them up in order to obtain the on-shell action for a general arbitrary rod structure. And probably equivariant localization is the most efficient technique for doing that. Then it would be nice to include higher derivative and quantum correction to each of these saddles to have a deeper insight into the quantum gravity regime. So far, we are just trying to classifying the saddles, trying to see what is the form of the saddles of this index and if they can compete. But of course, it would be nice to also compute the quantum corrections. And so again, the main result of the present talk was to classify, or at least provide a systematic construction of saddles of the gravitational index, assign chemical potentials and action, and show how this can be done systematically and in principle for any solution. In particular, we explored these different topologies that correspond, after taking the extremal limit, to the black ring, black lens, and topological solitons. And the main questions that remain are, well, first, we have this classification of possible candidate saddles, but we should ask which of these actually contributes to the index. I talked about solutions that have a complex matrix, complex gauge field. So possibly not all of these solutions are acceptable. There are different criteria that have been proposed, KSW criterion, the convergence criteria of the fugacities in the index, also the stability of probe d-branes in these solutions. So we can expand on this, of course, but so the question that remains is, what is the proper integration contour for our gravitational path integral? Which of these saddles are captured by the integration contours and which perhaps are not? So this is not a question that we know the answer so far. And also, I emphasize the role of these orbifolded solutions, where the horizon is an S3 mod Zn. They may play a role in the index, but this is still to be seen. And what is the role of topological solitons? That is, these solutions where the chemical potentials and the action become purely imaginary. If these should also be considered as saddles of the index in this regime or not. And once these questions have been answered, we can compare the saddles that are proper saddles of the index and study the quantum gravity phase diagram. Until when we have not established if the saddles are acceptable, this is maybe not such a safe question to answer. And finally, all this was from the point of view of the supergravity theory, the gravitational path integral. It is classical, or at best semi-classical. So we would like to match this with a microscopic computation, as it has been done in the asymptotical ADS case. So here, so far, we don't have any holography, so it would be perhaps nicer if we could connect all this story to some holographic setup. The holographic setup to be considered in this asymptotically flat context is the one of ADS3 CFT2. So it is possible to take a decoupling limit of these solutions, of these saddles. This has been emphasized in particular in the recent papers by Samir Murthy and collaborators, but the decoupling limit that I'm talking about is the one studied by Finn and many others in the 90s. So one can take this essentially the same decoupling limit and construct asymptotically ADS3 solutions out of these complexified saddles. There are also complexified solutions, but asymptotically they are still ADS3. And one can map the chemical potentials in this asymptotically flat setup to the chemical potentials that are normally defined in this ADS3 story, and then study the solutions in this context. So there is a map between the two. this is our current work in progress, but part of it has been already unraveled in recent papers. And one can put these saddles in relation with the fairy tale expansion, for instance, and see from this point of view which are the saddles that contribute. For instance, the question that we are trying to study, whether the black ring saddle should be seen as contributing to this partition function or not. So far, the answer is not really clear to us. So thank you for your attention.
Questions?
You mentioned that you didn't compute the action, but you could use the quantum statistical relation. In Wald's paper, after the formula for the entropy, that's kind of a corollary of his theorem there that the on-shell action satisfies the quantum statistical relation. So sometimes that's not even that's as good as computing it.
Yeah.
They're equal, so then it doesn't matter if you just compute the action by integrating the action or using the quantum statistical relation.
If you know that the quantum statistical relation is satisfied, if you know that, then of course computing the action, I mean, you can compute it either directly or by using the quantum statistical relation.
But do you know in your cases?
No, we don't know a priori in this complexified setup. We expect it is satisfied, and in the cases we studied, it is satisfied. We explicitly checked that.
Okay.
We know some version of thermodynamics is satisfied in this solution. So these solutions with bubbles outside of the domain of outer communication have these extra chemical potentials, these bubble potentials that are introduced that show up in the first law. So this has been studied by Conduri and Lucetti. So one can write down a first law and therefore, say, try to connect this to the quantum statistical relation. So there is a quantum statistical relation also in the presence of these non-trivial topologies. So this has been studied. But if this holds in full generality, this I don't know. But I would expect it does.
But without computing the action, you could check if the assumptions of that result by Wald.
Yeah, but these are complexified solutions. Maybe I should take a real slice of the solution that's possible. Yeah, in principle. Also, there is this Chern-Simons term that is not something that Wald considers normally, so you have to improve on that.
Okay, thank you.
The complication may come from that, so yeah.
More questions?
Sorry, could you elaborate why one should or should not include orbifolded solutions in the index? Are they not supposed to be smooth sometimes, or?
So I can give you. So so maybe you're asking why I'm hesitating about including these or not. In principle, they are part of the construction. They should be included. That's correct. I have just in mind the ADS5 case here. So in the ADS5 case, so part of this story goes through. It's not exactly the same construction, but still you have the black hole saddle, and then you can orbifold it by acting with an orbifold that acts on the Euclidean time circle and also on the circles associated with rotations in the external ADS and internal space. So there are some orbifolded saddles and some of them match the field theory dual. So there is a field theory dual and this Bethe ansatz approach that has been studied by people in the audience as well. So solutions to these Bethe ansatz equations are classified by some integers, and some of these integers precisely match this orbifold, the rank of the orbifold that is acting both on the Euclidean time circle and in the internal circles. So this is nice and it's there, but it's also known that there are other orbifolds that can be considered on the gravity side that don't have a match with the CFT Bethe ansatz construction. And so Aroni, Benini, Mamroud, and Milan, they studied stability criteria of D branes in these orbifold backgrounds, and they found that some of them are unstable towards nucleation of these D branes. And so they excluded them from from the class of saddles that should match the dual field theory. So have in mind something similar here. Maybe not all of these candidate saddles should be acceptable. So that's why I'm including them in the class that may or may not contribute to the index, because I have in mind this ADS5 case. But a priori, yeah, they are part of the construction.
More questions? Gee, people are getting less energetic, huh? No. Too many exciting things. So let's thank Davide.